mày. Dầm ra.
Nè bắn xích cho bồn nè. Ê Ấu nè.
Tốt.
Đồ nó cập nhật mấy những giải giả đi.
Ủa cập nhật cái gì đó?
Nhập iPad trên
iPhone đó hả?
đóng trên.
Mà cập nhật năm cũng bị giả.
Những giải giả nhìn giống Android.
Gì giống mình rồi.
In the summer of 18...
Đi.
Con.
Không chịu án. Mày xong ghê đó. Quánh cũng thật
Gà
đấy.
chưa? Ô gà chưa? Một đi. Chắn thì kiếm đã chưa?
Của Đào có tuổi mốt mới về à? Thứ 7 mới về à?
Nghĩa về chưa?
Nghĩa kêu bữa nhắn tin kêu thứ 2 mà.
Ủa kêu thứ 7 mà.
Bữa nhắn
Tao tưởng môn về,
thứ
tao
hai.
tưởng môn về sớm hơn nè.
Mà nhớ ra
Long gửi hình, tao tưởng mô hai thằng đó về sớm, cấp học cũng về sớm chứ.
Sớm
ủa chứ
sớm.
Nghĩa hình như Nghĩa đang quen bồ mới hay là quay lại về ta?
Quen bồ mới.
Quen bồ mới rồi chắc đang tỏ tình yêu rồi thứ 2 mới về.
Ủa đã đứa răng
con nữa.
biết cái gì đó. Nghĩa ngoan bộ
Ủa?
mới ở bộ đó.
Đăng story chính thấy à?
Settling
Đâu đăng
disputes
story đâu? Ủa chứ đăng story Đạt thấy
is
à?
a common sight in Demacia. Still, I
Ủa?
doubt any match will be as consequential as
Story
Trời
mà
ơi,
sao?
rất hay kìa.
first defeated his
Ủa,
brother Amicus.
Là Đăng, với Đăng chính lại hỏi là chữ quen bồ mới hay cũ là Đăng.
Thì bữa thấy lóc kẹt.
Lóc kẹt.
Con đi e flash được không?
Không đâu. Đâu có đăng story chó mà đâu. Tao lộn. Nhỏ. Tao lộn chứ nữa, đâu đăng story mà đâu. Tao lộn, lấy
Be
lúc
glad this
kẹt.
failure only
Nó lúc
ends
kẹt
in
mà.
embarrassment.
Tao lộn, đúng rồi, tao lộn.
Hồi nãy mình Đạt nói đăng story đó, anh em mình hiểu lầm đó nè.
Đâu có hay yêu lầm cái khùng. Bởi tao thấy lạ. Đăng đó, tao lộn á. Tao thấy lạ, đăng màn chính.
Má lạ hơn là Diệp Huy khóa IG luôn rồi. Má lạ nữa.
Ghê đó.
Chắc có chuyện gì rồi. Má mai đi làm rồi anh em ơi. Cuối cùng cũng kiếm được việc rồi. Ủa Long
tuyết
mi
gà.
Long mi làm bên kia không Long?
Cái gì?
Làm muốn làm bên kia người ta giới thiệu vô.
Là bên mố.
Ghi in kiểm duyệt nội dung.
Không chứ anh.
Kiểm duyệt nội dung.
Mạng đéo chịu an kìa. Bực quá.
Nhanh lòng.
Nè giờ nó đi hỏi làm rắn.
Đừng đánh nữa.
Đừng có đánh nữa.
Nhưng vẫn mua chuyện số gì kìa.
Để tôi. Vẫn đi ra nè.
Làm cute đó. Cute đó. Sai cào mãi sai cào. Lấy đồ gì mà ăn cào không đó. Nó ra đây nè, con ra đây nè. Đó. Ồ, ra đây mũ không mũ đó. 24 phút mẫn mũ nhiều rồi đó. Mua mũ không mua chỉ số phải. Bấm coi không. Mà em phun đồ luôn hắn á. Bấm vô người hắn á.
50 xác suất nhận gói nè. Hiểu không? Lính cháy lợn có cơ hội ra chỉ số mà. 28.
Ồ mình điển lạ đó. 28 chỉ số. Oh shit.
Phế rồi.
Mẹ như con trâu gì.
Ôi trời ôi trời ôi trời. Bắn cái kìa. Sao đạn hàng loạt mà.
A reminder that one's
Nhìn lông
plans
ấy.
never go unnoticed. Prepare yourself
Cái
for
mũ kìa.
Chết. Cứ bẩn bẩn người ta.
Trời
Ủa?
trời trời.
À quay. Không bên đây bắn hết rồi, bên đây mạnh lắm. Cái đạn hàng loạt mà.
Ồ trên ai kìa.
Ôi trời.
Để đi tốt.
Tốt.
Vô kìa.
Ai tốt luôn rồi, căng đó.
Chính tấu á. Chính tấu à. Rồi vô đây.
Ủa cái cờ Diệp Huy là cờ chi mà đẹp kìa ta.
Cờ hó.
Má.
Cờ hó thì ác tốt. Thầy vô gặt ăn liền đó bay.
Này gan rồi.
Thầy gặt.
Thầy gặt. Ôi trời.
Thầy vô gặt ngay. Thầy gắn gắn tại chỗ chết.
Mẹ chứ game bị tay gắn đúng mà. Rồi.
Ở nhà cả năm không ai biết. Ở nhà năm không ai biết. Chơi ném một lần mà thầy gắn tại chỗ luôn. Ô đem đồ ăn lâu quá trời. Anh chỉ cần thế thôi. Là bởi vì anh đã có em bên đời, vậy thì còn lắng lo chi.
1941, Florida doctor John Gorey faced a dire situation. Yellow fever, also known as the Black Vomit, was sweeping through his town, wiping out entire families. Patients came to Gorey's small infirmary jaundiced and burning with fevers up to 40 degrees Celsius. To cool his patients down, Gorey couldn't turn to refrigeration because that hadn't been invented yet. So he came up with the radical treatment. He suspended pans of ice in his infirmary, allowing the cool, dense air to flow down over his patients, providing much-needed relief. But this treatment was almost impossible to sustain because it required hundreds of kilograms of ice per day, and Gorey had only one way to get it. He relied on ice blocks that were transported thousands of kilometers through a now-forgotten ice empire, a vast network of ships and ice houses all built and controlled by one man, known to the world as the Ice King. Over the previous 35 years, he had forged a monopoly that spanned the globe, and anyone who wanted ice was at his mercy. Gorey only got a few deliveries each year, and now, by the peak of summer, the cost of just a few days' ice for the infirmary would have been more expensive than the average yearly wage, so locals began to refer to the ice as white gold. As Gorey's supply ran out, he was forced to watch his patients suffer and die. It was in that moment that he decided he would find a way to free the world from the grip of the Ice King. By the turn of the 19th century, most of America's ice came from the northern states, where thousands of square kilometers of lakes would freeze over for much of the year. The hard part was getting all that ice out.
To get ice out of a lake or river, first of all, you had to trust that it was deep enough to support your weight. Then there's no way to really tell. Then you had to walk out several feet onto this plane of ice, take a saw that's as long as I am tall, and then carve the very ice that you're standing on and just, hope to heaven that it doesn't sink. Then you had to kind of float it to shore, and a horse would help to kind of pull the ice into the back of a wagon. It was frequently common for the harvesters and their horses to fall through into the ice, sometimes to their death.
This dangerous and painstaking process meant that ice remained a rare commodity, available mostly to wealthy landowners. One of the few who had access to it was 22-year-old Boston merchant Frederick Tudor. In the winter of 1805, Tudor was thinking back to a tragic incident that had happened 4 years earlier. He and his brother came down with a bad fever while visiting the Caribbean. Back home, they would have just asked their servants to get some ice. But on the islands, ice was unheard of. With no way to cool down, the brothers cut their trip short and returned to America. And while Frederick recovered, his brother did not. Today, we know that ice wouldn't have saved his brother's life because he likely suffered from a rare case of bone tuberculosis. But at the time, Tudor believed that it was the lack of ice on the islands that was responsible for his brother's death. It was this painful memory that gave him an idea. What if he could be the one to bring ice to the Caribbean and, in the process, make his fortune? So Tudor got to work. He hired dozens of men to gather ice and approached investors to help finance a ship. But to the investors, this plan seemed ridiculous. Tudor wrote, "People only laugh when I tell them I'm going to carry ice to the West Indies," which is understandable because the journey would take 3 weeks, sailing through warm seas under the blazing Caribbean sun. I mean, can you really transport ice in those conditions for that long? Wouldn't it all just melt? It turns out, people had figured out ways to make ice last a long time, even thousands of years ago. As far back as 500 BC, in the scorching summers of the Persian Empire, ancient kings like Xerxes enjoyed refreshing frozen desserts, even when the outside temperature climbed as high as 35 degrees Celsius. Now, ice in the desert might seem strange, but during the winter months, temperatures can drop dramatically. So the Persians filled shallow pools with water, which would freeze overnight, and in the morning, they would break up the ice sheets and collect the pieces. To make that ice last until the summer, they used 3 key techniques.
let's try a simple experiment. I have 8 ice cubes spread evenly in one dish here, and I have another 8 ice cubes now stacked together in one mega cube in this dish over here. Now, if you leave these 2 plates to melt for a few hours, the stacked ice cubes fare a lot better. And that's because the main way ice melts is through heat conduction on its surface. So even though the volume was the same, the surface area exposed here is double what we had here. The key idea here is that you want to pack your ice as tightly as possible.
In fact, the best shape to minimize the surface area is a sphere. So if you think about it, a snowman is pretty much mathematically optimal to survive as long as possible. But you don't need perfect geometry to make ice last a long time. In the winter of 2010, the city of Helsinki dumped all the snow plowed from their streets onto this huge pile, around 30 meters high and 100 meters wide. Almost a year later, that very same pile was still around, despite being exposed to one of the country's hottest summers in decades. The main reason it lasted so long is because the ratio of surface area to volume actually decreases for larger and larger amounts of ice. For example, if you double the radius of this snowman, then the volume of ice increases by a factor of 2 cubed, or 8, but the surface area only increases by a factor of 2 squared, or 4. This is known as the square-cubed law, which was the second technique used by the Persians. And finally, they needed a way to shield the ice from the harsh desert.
Okay, I have another example. 2 ice cubes, 2 dishes. The only difference really is going to be that I have this fan, which is going to be blowing air onto this ice cube. Now, it's not heating any of the air, it's just blowing away any air the ice would have chilled for itself, and it's introducing more warmer ambient temperature air, which heats the ice cube better. After about an hour of the fan blowing, this ice cube is completely gone, whereas this one is only about 40% melted. So obviously you want to minimize the amount of airflow that you're getting around your ice. One way you can do that is by putting the ice in a deeper dish, like a pit. Because colder air sinks to the bottom, so it collects around the ice and lets it stay there for longer. And a way you can one-up that is to seal the ice, which is exactly what the Persians did.
This is a yakhchal, an ancient Persian ice house. It's a massive domed structure with walls up to 2 meters thick at the base. Here, the Persians collected up to 220 tons of ice and packed it tightly together in a pit. This allowed the cold, dense air to collect while warm air was funneled up and out of the dome. After the winter, the entire structure was sealed up, insulating the ice until summer. For the next 2,300 years, these techniques barely changed. And now, Tudor was ready to bet his fortune on these ancient principles. So he mortgaged land on his family estate to buy a ship, and he began modifying it for the long journey to the West Indies.
He did that by building out a cargo hull in a ship that was built similarly to the ice houses. The ice was elevated off the ground, so it wasn't sitting in meltwater, because meltwater, speeds up the melting of ice. And the blocks of ice were also packed really tightly.
Tudor went all in, sinking a full $10,000 of mostly borrowed money into the venture, which is the equivalent of over $250,000 today. He sent his youngest brother and his cousin ahead to the island of Martinique to build an ice house ready to receive the cargo. On the morning of February 13, 1806, Tudor departed Boston Harbor, carrying with him over 80 metric tons of ice, the first shipment of its kind. The Boston Gazette ran an article that read, "No joke, a vessel has cleared at the custom house with a cargo of ice. We hope this will not prove a slippery speculation." After nearly 3 weeks at sea, Tudor's ship arrived, and to his relief, around half of the ice had survived the trip. But there was a problem. His brother and cousin had failed to build an ice house. So with no place to store the ice, Tudor had to sell it straight off the dock under the hot sun. He sold as quickly as possible, but after 2 days, he had only made about $50. The locals were confused by the strange frozen water, and many were shocked when their new product disappeared before their eyes. One customer tried to save his precious ice by submerging it in a bath of water, only to find it vanishing even faster. In the end, all Tudor could do was watch his remaining ice melt away. Yet somehow, he was undeterred, and over the next 4 years, he continued to borrow money, using every cent to ship ice to new markets like Cuba, Jamaica, Barbados, and Antigua. But business remained difficult. Tudor wrote, "I found myself without money and without friends, and with only a cargo of ice in a torrid zone to depend on for the supply of both." By 1809, Tudor owed $40,000 to investors, which is over $1 million today. He was hounded by creditors. He was forced to hide from sheriffs on his own ships, and he was even sent to debtor's prison twice. He later described it as the winter of my discontent, but during that time, he had a revelation. The reason demand wasn't picking up was because the people of the West Indies didn't know what to do with ice. So all he had to do, he reasoned, was make them understand by offering them some refreshing drinks.
He convinces the bartenders there to let him show them how to make icy cocktails. And he gives the ice initially to the bartenders for free. So the bartenders can sell both the icy drink and the room temperature drink at the same price, just to see what their customers prefer. And lo and behold, they prefer the icy drink.
In Tudor's own words, a man who has drank his drinks cold at the same expense for 1 week can never be presented with them warm again.
Tudor even showed them how to make ice cream, which became an instant hit, especially in Cuba. 150 years later, during the Cuban Revolution, its leader, Fidel Castro, was obsessed with ice cream. He was actually known to eat up to 18 scoops after lunchtime, which is a bit crazy. His sweet tooth was so famous that the CIA actually tried to assassinate him with a poisoned milkshake. Now, back in Tudor's day, his work was finally paying off. The cafe owners in the West Indies started asking him for more and more ice, and he realized that he could increase his profits just by refining his methods. So he started using sawdust to insulate his ice on the ships, because sawdust was a phenomenal insulator that you could basically get for free from all the sawmills around Boston. They were just trying to get rid of it. And he also replaced the manual saws at the lakes with horse-drawn plows, which made it all the easier to get the ice out. Because of that, the price of extracting a ton of ice dropped from around 30 cents all the way down to 10 cents.
By the 1820s, Tudor was finally turning a profit, and the ice trade began to pick up. So much so that copycat businesses began to crop up. But Tudor wasn't about to let anyone else have a share of the market he created, so to maintain his monopoly, he often undercut his competition until they either gave up or went out of business. Tudor's ambition didn't end there, and he wrote that there was an experiment I've been desirous of making for 20 years. In 1833, he took on his biggest challenge yet, a 4-month journey to ship ice halfway across the world to Calcutta, India. And despite the trip being 5 times longer than his first one to the Caribbean, more than half of the ice survived. In India, the ice was a big hit. Over the next 20 years, Tudor made around $220,000 in Calcutta alone, making it one of his most profitable ventures. Over that same period, he rapidly expanded his empire, opening routes to Brazil, Singapore, Hong Kong, and even Australia. His yearly sales went from less than 10,000 tons in the 1830s to a record high of 132,000 tons in 1856. Seeing the wealth and power of his monopoly, the world gave Tudor a new name, the Ice King. In under 50 years, the ice trade had become one of the largest industries in the US and its second largest export by weight. What was once a luxury product became a commodity. By the 1860s, devices known as ice boxes started popping up in ordinary kitchens. Essentially, they were insulated wooden cabinets with a compartment for ice at the top, which would then cool down the food underneath, keeping it fresh. Families across the country soon bought ice daily or weekly, with the average New Yorker buying over 600 kilograms a year. This surge in demand resulted in a curious new profession, the Iceman. The Iceman would go door to door delivering huge blocks of ice up to 45 kilograms. And while home delivery was nothing new in the 19th century, the Iceman was unique in that he needed to go inside your house to make his delivery.
All kinds of rumors and jokes and cultural thoughts started to crop up. And if you look at some of the most popular songs at the time, she fell in love with the Iceman, or the Iceman took my wife. If you look at old Valentine's Day cards that were circulating at this time, they all had puns about the Iceman. You know, the Iceman made my wife, you know, too hot. He was supposed to deliver ice. Like, it was so silly.
Consumption of ice in big cities like New York skyrocketed. And by the end of the 19th century, ice had grown into a billion-dollar business. And while part of the demand was due to home ice boxes, the real driving force was several new industries.
The ice industry also launched the fish industry, the meatpacking industry, the brewery industry. It became like this multi-level industry. When we get to the point where there are railroads, then comes the invention of the refrigeration car, railroad cars that were insulated with ice blocks to carry things that are perishable.
So if you think about it, fresh fruits and vegetables that have been region locked now can become national staples. So you have apricots and cherries from California, you have strawberries from Florida. They can all go inland. Actually, you want to guess the name of a vegetable that was really popularized with these chilled cars?
Chilled vegetable. I'm gonna guess lettuce?
Well, which one?
Iceberg. It's gotta be iceberg, right?
Exactly.
You know, it's like crunchy water. It's like ice, iceberg lettuce.
It is crunchy water, but it was actually called iceberg because of the ice that kept it fresh.
This change marked the beginning of a new system called the cold chain. And for the meatpacking industry, it was a huge upgrade. Previously, the only way to transport fresh meat was by sending rail cars filled with live cattle straight from farms to cities. Then the animals had to be brought into the city and held in local stockyards before they were prepared by local slaughterhouses and butchers. The result was that city centers were filled with dirty, noisy cows. And on top of that, since almost half of the animal was inedible, shipping was extremely inefficient, pushing up the cost. But with chilled rail cars, all this changed, and the country's supply chain reorganized into three parts. First, ranches across the Great Plains funneled their cattle to cities in the Midwest. Taking on the role of industrial food preparation and distribution, these cities built up vast stockyards, slaughterhouses, and rail hubs to send the meat onward. Chicago emerged as the nation's meatpacking capital, ballooning in size from just 30,000 people in 1850 to 1.7 million in 1900. And at the end of the chain were the large, insatiable cities. With the new system in place, almost twice as much edible meat could be transported in each rail car, eventually dropping the cost in urban areas by 39%. As a result, demand soared. In New York City alone, beef shipments rose from just 2,400 tons in 1882 to around 63,000 tons in 1886. That's a 25-fold increase in just 4 years. But more importantly, with a national distribution network to rely on, these cities no longer needed to prepare meat locally. They could finally get rid of all the infrastructure and herds of cows in the city center, freeing up the land for things like housing, offices, and factories. This fundamentally changed their structure and gave rise to the modern city of today. But while the cold chain was redefining America, a new invention was about to overthrow the natural ice industry. Which brings us back to Dr. John Gorrie in the 1840s. A few scientists had devised and even built prototype cooling machines, but they weren't commercially viable. And Gorrie wasn't faring any better. He had spent 3 years struggling to make artificial ice with no success. But one night, while experimenting with an air pump to drain a bucket, he noticed that if he let the air expand quickly, it formed a thin layer of ice on the surface of the water. He had just stumbled upon the breakthrough he needed, and he set about creating a prototype based on this idea. Take a sealed cylinder filled with air and a piston that can move inside it. We'll assume there's no friction or heat loss to the environment. When the piston pushes down, the air is compressed, increasing its pressure and temperature. The reason the temperature increases is because as the piston pushes down, it moves toward the air molecules. So when a molecule bounces off this moving surface, it gains a little bit of speed. And since the temperature is proportional to the molecule's speed squared, well, the air must heat up. But notice that this process is completely reversible. If the piston is released, the high-pressure air pushes the piston back until the pressure equalizes. So now when one of the molecules bounces off the piston, it loses a little bit of speed. Gorrie knew that if he simply let all of this hot, high-pressure air expand, it would return back to roughly its original temperature, which wouldn't be very helpful. But what if He first cooled the air and then let it expand. Well, then its temperature would drop far lower than the ambient air. He started with a similar setup, a cylinder and a piston that were powered by a hand crank, which he then attached to a large air tank. As Gory turned the crank, the piston moved down, compressing the air and raising its temperature. To prevent the air from being sucked out of the large tank, Gory added a one-way valve at the bottom of the cylinder. He also added a similar valve at the top of the piston so that the cylinder could refill with fresh air. So now, with each turn of the crank, more and more air was added to the tank, which allowed Gory to increase the pressure to around 10 atmospheres. But then he added one extra step. In between the piston and the tank, he placed a big bucket of water, and he forced the air through a submerged pipe. This cooled the air down to around the same temperature as the water. The result was that his tank was still filled with high-pressure air, but instead of being hot, it was cool. So now, when Gory released some of his cool air into another cylinder with a piston, the air rapidly expanded. This cooled the air down below its starting point and dropped it to freezing temperatures. Gory then placed this entire cylinder inside a large tank of water, finally making ice. But to avoid the entire tank freezing solid and clogging up his machine, he used one final trick. Instead of fresh water, he filled the final tank with salt water, which freezes below 0 degrees Celsius. Since the salt water remained liquid, he then submerged metal molds of fresh water until they froze into solid blocks, essentially creating the world's first ice cube tray. For the first time ever, ice could be created anywhere, even in the heat of the Florida summer.
And when he, says to the world, like, I've invented ice, the reaction was, the hell you have? But no man should be creating ice. Only God can create ice. And what John Gory also didn't realize is that in the first public venues in which he announces his ice machine, Frederick Tudor has his associates in the audience. And Frederick Tudor is a man who does not take lightly to threats to his empire. And what bigger threat to the, natural ice harvesting empire is there than human-made ice?
There was no way the Ice King was giving up his empire without a fight.
What he ends up doing is he ends up paying editors up and down the eastern seaboard at newspapers to publish scandalous news articles about John Gory. So everywhere from Tallahassee up to New York, you see newspapers publishing headlines like, there's this crank that thinks he can make ice as good as God Almighty. And ultimately, John Gory, he does patent his machine, but he never makes a dime on it.
Gory spent the next few years in financial ruin. A decade later, he died alone and penniless, most likely succumbing to malaria. There are reports he suffered an extremely high fever in his final days, the very symptom he had tried to alleviate for so many years. But Gory's invention hadn't been completely ignored. Soon, others began work on artificial cooling machines, including James Harrison, a Scottish-born engineer working in Australia. Harrison noticed that Gory's machine had one big drawback. It relied on just two components to move heat, a compressor and an expansion engine. So instead of using air to cool his machine, he tried a different approach.
I have a can of freeze spray here, which is a liquid that when I press down on this button, comes out and immediately evaporates into a very, very low temperature gas. So what I'm gonna do is I'm gonna blast it at this cup of water, and the process is actually so effective that in essentially under a minute, I'm able to get some ice to form in there. Okay, so after a layer of water, what you get is a bunch of ice. Now, the reason this works is because something special happens when a substance changes phase. So in order to go from a liquid to a gas, it needs to absorb a lot of energy. And pretty much all this energy goes into overcoming the force of attraction between molecules so that they can disperse and go into the gas phase. Harrison realized he could take advantage of this effect by forcing a fluid to continuously evaporate and condense as it's going through a loop. A modern version looks something like this.
Start by adding a liquid under high pressure to a loop. Passing this liquid through an expansion valve quickly drops the pressure and temperature, causing some of the liquid to immediately turn into a gas. The mixture then passes into an evaporator coil where the remaining liquid continues to boil. But this phase change requires a lot of energy, so the liquid absorbs heat from the environment, and this is what creates the cooling effect. The cold gas is then cycled through a compressor, raising its temperature, and then it's pushed through a condenser coil. Here, the hot gas cools and turns back into a liquid, releasing the absorbed heat back into the environment, before returning to the expansion valve. By repeating this cycle over and over again, Harrison was reportedly able to manufacture as much as 3,000 kilograms of ice per day, and his machine was a huge commercial success.
Meanwhile, public resistance to godless ice and artificial cooling began to fade, overshadowed by a growing health crisis linked to natural ice. One of the reasons artificial ice was so much better is because we make it on our own terms. With natural ice, we had to wait until the right season, in the right place, and then whatever happened in the water that froze, like something died or was rotting in there, you had to work with it.
By the time we get to the mid-19th century, the peak of the Industrial Revolution, factories and farms just letting loose their chemicals and detritus into the nearby lakes and rivers.
You put an ice block into your cocktail, you could get cholera. There are like stories of hospitals treating wounds with ice, and then the ice makes you get a disease, and your wound isn't even the problem.
They're getting cholera, they're getting food poisoning or ice poisoning. I mean, they're getting very, very sick.
It's so funny, when we were first talking about this story, I was thinking about this, frozen New England ice, and I was just imagining like the purest lake water, this crystal clear ice, and like just this incredible product, right? But now that you mention it, it probably is a lot less hygienic, and there's probably germs in there.
And so the, human-made ice companies were like, sure, our ice isn't made by God, but natural ice will kill you. So which one do you want?
After the first affordable home refrigerator landed in the mass market in 1927, it became one of the fastest adopted new technologies of the entire 20th century, going from less than 1% of homes having one in the 1920s to 85% by 1944. This made its takeoff even faster than the motor car replacing the horse-drawn cart.
There's this argument of, would the world really be so different without refrigeration? Sure, food, strawberries, iceberg lettuce, but then you think about vaccines, blood donations, insulin, the same cold chain transports those things. And then beyond medicine, the same principles that Harrison and Gore used for their fridges are what allow us to cool things down to almost absolute zero. Over the past century, so many of the discoveries that we made rely on this principle of refrigeration. MRIs, the Large Hadron Collider at CERN, the James Webb Telescope, all of that is also refrigeration. And my favorite is the PCR story, where Thermus Aquaticus was in a fridge for 16 years before Kary Mullis discovered it. There wouldn't have been that connection to make PCR viable in that way without a fridge.
I think it's easier to focus on the movement of macroscopic objects and macroscopic things happening, but this is really about controlling motion on the smallest scale, controlling thermal motion, which is a pretty remarkable breakthrough. I mean, we can heat things up for a long time, so you want to increase the thermal energy of molecules. You could do that from the time we had fire. But actually taking those molecules and figuring out how to remove their thermal energy and really slow them down, that's the refrigeration story, and that's really recent. But as you point out, it has profound effects.
Gore was able to make ice because he wasn't afraid to step outside his own profession, medicine, and venture into a new field, thermodynamics. And while you probably don't need to reinvent the fridge, learning a new skill is always fun. Here at Veritasium, we create simulations and models to test our ideas and illustrate them. And along the way, our team has learned to code in Python to make sure our animations are as accurate as possible. So if you, like us, want to understand coding and strengthen your programming skills, a great place to start is today's video sponsor, Brilliant. Brilliant have recently added new Python and coding courses, starting from the basics and working all the way up to complex topics like how AI works. Each of these is designed to break down concepts into smaller pieces, train your intuition, and encourage you to explore your own ideas. Brilliant helps you build skills in math, science, and computer science through step-by-step interactive learning. This method is proven to be far more effective than just watching lectures or videos alone. What I love most is that instead of dumping formulas on you, Brilliant guides you to those aha moments where everything finally clicks. You know, I have changed my phone a fair few times over the past 5 years, but every time I do, I make sure to download the Brilliant app because it's such a great way to keep my brain engaged. So if you want free access to Brilliant courses for a full 30 days, go to brilliant.org/Veritasium. You can scan this QR code or click the link in the description. Brilliant also gives our viewers 20% off an annual premium subscription for unlimited access. So I want to thank Brilliant for sponsoring this video, and I want to thank you for watching.
What would happen if a star exploded near the Earth? Well, the nearest star to Earth, of course, is the Sun, and it is not going to explode. But if it had 8 times the mass, then it would go supernova at the end of its life. So what would that look like? Well, as noted by XKCD, if you held up a hydrogen bomb right to your eyeball and detonated it, that explosion would still be 1 billion times less bright than watching the Sun go supernova from Earth. That's how insanely powerful supernova explosions are. They are the biggest explosions in the universe. When we see supernovae in other galaxies, they are brighter than the combined light of hundreds of billions of stars. So bright, in fact, that they appear to come out of nowhere. On the 8th of October 1604, the astronomer Johannes Kepler looked up into the night sky and noticed a bright star he had never seen before. It was brighter than all the other stars in the sky, about as bright as the planet Jupiter. On moonless nights, it was bright enough to cast a shadow. Kepler published his observations of this star in a book called De Stella Nova, which means about a new star in Latin. Kepler thought he was witnessing the birth of a new star, but it was actually a star's violent death. Over the following year and a half, the light faded until it was no longer visible. But the name stuck. Even once we learned what was really happening in the 1930s, the violent final explosion for stars between about 8 and 30 solar masses has been called a supernova. But how exactly a star explodes is not what most people think. For most of a star's life, it exists in a stable balance. In its core, it fuses lighter elements together to make heavier ones, and in the process, it converts a small amount of matter into energy. This energy is really what keeps the star from collapsing in on itself. Gravity compresses the star, but that force is counteracted by the pressure generated by the movement of particles inside the star, and by the pressure of photons released by fusion. So, in effect, stars are propped up by their own light. If the rate of fusion drops at the center of the star, the temperature and the pressure decrease. Gravity starts winning, compressing the star. But this increases the temperature and pressure in the core, which increases the rate of fusion. It's a stable, self-regulating system. But there's a problem. Stars have a finite amount of fuel, which over time gets used up. Our sun is about 5 billion years into its 10 billion year lifespan. There are stars dozens of times more massive than the sun, which you would think would live much longer, but they actually use up their nuclear fuel faster. A star 20 times the mass of our sun has a lifespan of just 10 million years. And more massive stars burn hotter and even brighter, but for much shorter lives. For 90% the life of a star, the core is only hot enough to fuse hydrogen into helium. And when the hydrogen runs out, fusion slows, gravity compresses the core, and its temperature increases to 200 million degrees, at which point helium fuses into carbon. There's enough helium to power the star for around 1 million years, but as the helium runs out, the core is again compressed and heated. Carbon starts fusing into neon, which lasts about 1,000 years, and then neon fuses into oxygen for a few more years, then oxygen to silicon for a few months, and at 2.5 billion degrees, silicon fuses into nickel, which decays into iron.
Now, at the heart of this giant star, there is an iron core building, only a few thousand kilometers across. Iron is where this pattern stops. Instead of liberating energy as it fuses into heavier elements, it actually requires energy. Iron is the most stable element, so it actually takes energy both to fuse it into heavier elements and to break it down into lighter ones. Both fusion and fission reactions ultimately end up at iron. The iron core grows, but the crush of gravity becomes greater and greater as the rate of fusion drops. When the iron core is about 1.4 times the mass of our sun, which is known as the Chandrasekhar limit, the pull of gravity is so strong that something totally wild happens. Quantum mechanics takes over. Electrons run out of room to move, and they're forced into their lowest energy states. They then become absorbed by the protons in the nucleus. In this process, the protons turn into neutrons and release neutrinos. With the electrons gone, the core collapses, and fast, at about 25% the speed of light. So what used to be a ball of iron 3,000 kilometers in diameter becomes a ball of neutrons just 30 kilometers across. Essentially, it's a neutron star. With no outward pressure to hold it up, the rest of the star caves in, also falling at a quarter the speed of light. It hits the neutron star and bounces off, creating a huge pressure wave. But this kinetic energy isn't quite enough to start a supernova explosion. No, the thing that really kicks it off is the humble neutrino. Now, I normally think of neutrinos as particles that do basically nothing. I mean, they interact so rarely with matter that right now, there are 100 trillion neutrinos passing through your body per second. It would take a light year of lead just to give you a 50-50 chance of stopping a neutrino. And that's because they interact only through gravity and the weak force. But in a supernova, when the electrons are captured by the protons, an unbelievable number of neutrinos is released, around 10 to the 58. You would think they would just fly off at nearly the speed of light, but the core of a supernova is incredibly dense, about 10 trillion times more dense than lead. And as a result, it traps some of those neutrinos and captures their energy. And this is what makes a star go supernova. A particle that is millions of times less massive than an electron, that barely interacts with anything, is responsible for some of the largest explosions in the universe. In that explosion, only 1/100th of 1% of the energy is released as electromagnetic radiation, the light that we can see. Even then, supernovae have enough energy to outshine a whole galaxy. About 1% of the energy is released as the kinetic energy of the exploding matter, but the vast majority of the energy is released in the form of neutrinos. And neutrinos are actually the first signal we detect from supernovae. And that's because after they're generated in the core, they can escape before the shockwave reaches the surface, where the light that we see is generated. So neutrinos can arrive on Earth hours before the photons, giving astronomers a chance to aim their telescopes at the right part of the sky.
I actually used to work at a neutrino observatory back in college, and I would work the graveyard shift between midnight and 8 a.m. So if I detected a really big increase in the neutrino flux during my shift, it was my job to call and wake up scientists so they could go look out for a supernova. Now that never actually happened, but we did have some close calls.
Now, I need to clarify a couple things. First, not all really massive stars explode. As they collapse, some form black holes instead, which means they do not go supernova. And second, there's another way to make a supernova. Sometimes a white dwarf star, which is incredibly dense, pulls matter off a nearby star. And when its mass reaches that Chandrasekhar limit of 1.4 solar masses, the white dwarf collapses, creating a supernova. This is actually the type of supernova that Kepler saw in 1604, a supernova 20,000 light years from Earth. Now, because the shocks are asymmetric, supernova explain neutron stars that can move really fast. There's a neutron star we've observed with a velocity of 1,600 kilometers per second. and we think that was caused by a very asymmetric supernova explosion, shooting off in the other direction. Despite only recently learning about how supernovae work, humans have been observing them for thousands of years. Ancient Indian, Chinese, Arabic, and European astronomers all observed supernovae. But they are quite rare. In a galaxy like our Milky Way, consisting of 100 billion stars, there are only about 1 or 2 supernovae per century. A particularly amazing example is the supernova of 1054, when the light of a supernova 6,500 light years away reached the Earth and was recorded by Chinese astronomers. If we look to where that supernova was recorded, we see the Crab Nebula. It is a giant remnant of radioactive matter left behind by the explosion. In the 1,000 years since the explosion, the remnant has grown to 11 light years in diameter. Supernovas produce a lot of cosmic rays. Cosmic rays are actually particles, mainly protons and helium nuclei, and they travel out at very, very nearly the speed of light. They have a tremendous amount of energy. So, at what distance could a supernova cause problems for life on Earth? Well, the closest stars to us, besides the Sun, are the 3 stars in Alpha Centauri. They are 4.4 light years away. But stars do move around, and on average, a star gets within 1 light year of Earth every 500,000 years. So what would happen if such a star went off?
Yeah, so within a light year, you're easily within a danger distance from just the kinetic energy. So I think even at that distance, you're looking at possibly pulling the atmosphere.
But we would also have other problems to worry about. Supernovae create conditions that are hot enough to fuse elements heavier than iron. In the months after the explosion, these elements undergo radioactive decay, producing gamma rays and cosmic rays. Less than 0.1% of the energy produced by a supernova is emitted as gamma rays from these radioactive decays, but even this tiny percentage can be dangerous. At a few light years from a supernova, the radiation could be deadly, though most of it would be blocked by our atmosphere.
Now, the Earth is protected from solar and cosmic radiation by our atmosphere, and specifically by ozone molecules, 3 oxygen atoms bonded together. But high-energy cosmic rays from supernovae can come down and break apart nitrogen molecules in the atmosphere. And then these bond with oxygen atoms, which can then break apart ozone. And so we can lose a lot of our ozone if there's too many cosmic rays coming from supernova events, and that can expose us to all kinds of dangerous radiation coming in from space. We actually see an increase in atmospheric NO3 concentrations coinciding with supernova explosions.
A supernova within 30 light years is rare, only happening maybe once every 1.5 billion years or so. But a recent article suggests supernovae could be lethal all the way out to 150 light years away, and so those would be much more common. We actually have evidence for a supernova that went off 150 light years from Earth 2.6 million years ago. It would have been seen by our early human ancestors, like Australopithecus. And we know this because there are elements present on Earth that could only have been deposited by a recent supernova. In sedimentary rocks at the bottom of the Pacific Ocean, scientists found traces of iron-60 in a layer that was deposited 2.6 million years ago. Iron-60 is an isotope of iron with 4 more neutrons than the most common type of iron. Iron-60 is really hard to make. Our sun doesn't make it, nor is it produced basically anywhere else in the solar system. Iron-60 is made basically exclusively in supernova explosions. And iron-60 is radioactive. It has a half-life of 2.6 million years. So every 2.6 million years, half of the sample decays into cobalt-60. So all of the iron-60 that was around during the formation of the Earth 4.5 billion years ago has definitely decayed. So the iron-60 that the scientists measure is proof of a recent supernova. Scientists also measured trace amounts of manganese-53 in the same sediments, giving further evidence supporting the idea that recently there was an explosion of a nearby supernova. The supernova that happened 2.6 million years ago wasn't catastrophic for our ancestors. but some researchers hypothesized that it could be related to the mass extinction which is seen at the Pliocene-Pleistocene boundary in the fossil record around the same time. This extinction wiped out around a third of marine megafauna. The idea is that the cosmic rays from the supernova hit particles in our atmosphere, creating muons, which are charged particles like the electron, only more than 200 times heavier. The muon flux for years after the supernova would have been 150 times higher than normal. And the bigger the animal, the larger the radiation dose it would have received from these muons, which is why megafauna were so disproportionately affected. And what's more, the animals that lived in shallower waters were more likely to become extinct compared to the ones that lived at depth, where the water would have protected them from muons. Further evidence for these recent nearby supernovae comes from our place in the galaxy. You know, if you look in the space between the stars in our galaxy, on average there are around 1 million hydrogen atoms per cubic meter. That may sound like a lot, but it's basically a perfect vacuum. But for hundreds of light years in all directions around our solar system, you find there are 1,000 times fewer hydrogen atoms. It's like they've all been blown out somewhere, and our solar system is existing in this cosmic void inside a low-density bubble. So that is evidence for maybe tens of supernovae that would have blown all this material outwards. But there are cosmic explosions that are even more deadly than normal supernovae: gamma-ray bursts. Gamma-ray bursts were discovered by the Vela satellites, which were looking for Soviet nuclear tests. But on the 2nd of July, 1967, the satellites detected a large burst of gamma rays which were coming from space. There are two main sources of gamma-ray bursts: mergers of neutron stars and the core collapses of gigantic stars called hypernovae. Hypernovae are caused by stars that are at least 30 solar masses and rapidly spinning. Their collapse leads to an explosion 10 times more powerful than a regular supernova, and it leaves behind a black hole. The gamma-ray bursts caused by hypernovae channel most of their energy into beams which are just a few degrees across. If there was a gamma-ray burst within 6,000 light years, it would decrease the ozone level enough that it could be catastrophic. To put this distance in context, a sphere with a radius of 6,000 light years contains hundreds of millions of stars. On October 9th, 2022, astronomers detected one of the most powerful gamma-ray bursts ever measured. It was powerful enough to measurably affect how the ionosphere bounces radio waves. The effect on the ionosphere was around the same as a solar flare. But this gamma-ray burst was located in a galaxy 2.5 billion light-years away. Astronomers speculate that a gamma-ray burst could have caused the late Ordovician mass extinction, which wiped out 85% of marine species 440 million years ago. There is no direct evidence, but gamma-ray bursts are common enough that it is estimated that there's been a 50% chance that there was an ozone-removing, extinction-causing GRB in the vicinity of Earth in the last 500 million years. So, if a supernova or a gamma-ray burst were to go off near the Earth now, that would be pretty catastrophic. But in an ironic twist, we kind of owe our existence to these sorts of explosions. Because 4.6 billion years ago, it was probably the shockwave from a nearby supernova which triggered the collapse of a cloud of gas and dust that gradually coalesced to form our solar system. So the sun, the earth, and all of us wouldn't be here today without the explosions of nearby stars.
Figuring out how supernovae explode was incredibly difficult. It took a combination of astrophysics, particle physics, computer science, and mathematics. And if you want to develop a better understanding of our universe, then you should check out the sponsor of this video, Brilliant. Just go to brilliant.org/Veritasium and you can get started for free right now. Brilliant is an interactive learning tool that uses a hands-on approach to teach you a wide range of STEM concepts. You know, watching a video can give you a good overview of a topic, but if you really want to have a deep understanding, you need to learn interactively and test yourself from the foundations up. Brilliant offers simulations to manipulate and quizzes to master any new subject. There are thousands of lessons to explore, ranging from the foundations of math to cosmology and quantum mechanics. And there are new exclusive lessons released every month. Brilliant is the best way to learn something new every day, and there's no better time to start. The first 200 people to sign up at brilliant.org/Veritasium get 20% off an annual premium subscription. So I want to thank Brilliant for supporting Veritasium, and I want to thank you for watching.
Arthur C. Clarke had a sequel to 2001: A Space Odyssey. It's called 2010 Odyssey 2. And at the end of it, an alien intelligence converts Jupiter into a star. As a group of astronauts narrowly escape the implosion, they receive the following message from the aliens. All these worlds are yours, except Europa. Attempt no landing there.
Now, that was just a novel, but it suggests that already in 1982, we suspected that Europa might offer our best chance of finding alien life in our solar system.
42 years later, in October 2024, NASA is actually launching the most advanced mission to hunt for signs of alien life. And it's going to Jupiter's moon, Europa. There's just one problem. Jupiter kills everything around it. So how could life even exist there? And how do you make a probe that can withstand the perilous conditions? Deep inside Jupiter, there is so much pressure that hydrogen is believed to take the form of a metallic liquid. And this metallic liquid hydrogen generates an incredibly powerful magnetic field, almost 20,000 times stronger than Earth if you measure at the same distance away. So if you could see this magnetic field from Earth, it would appear twice as big as the full moon. On its own, that magnetic field is harmless. But right in the middle of it is the most volcanically active world in the solar system, Jupiter's moon, Io. The volcanoes on Io's surface shoot out tons of sulfur dioxide, and every second, 1 ton of this material gets ionized and trapped inside Jupiter's magnetic field. And the field accelerates these particles to rotate incredibly fast with Jupiter, so they whiz around at over 300 kilometers per second. Their inertia actually pulls back on the field, stretching it out. And this trapped material slams into other moons, ejecting even more particles from their surfaces. This cycle forms massive radiation belts which span past Europa and the other moons of Jupiter.
Now, for electronics, this intense radiation is kryptonite.
In the 1970s, the Pioneer 10 and Voyager missions only briefly passed by Jupiter, but the radiation caused glitches, gave the instruments false commands, and corrupted some of their data. Even with modern shielding, a spacecraft within the radiation belts would only survive for around 3 months. So how will NASA's new mission, the Europa Clipper, orbit Europa for over 4 years without getting fried? Well, the solution is it won't.
It'll orbit Jupiter from afar and then swoop in every few weeks to quickly fly by Europa and then leave again. And since the mission is going to collect a lot of data, it can use the downtime while it's way out here to transmit it all back to Earth before going in for another swoop. In all, it'll do 49 flybys, mapping almost the entire surface. That's actually how the Clipper got its name, after the fast and nimble 19th century Clipper ships, quickly dipping in and out of ports. But of all the places in the solar system to look for life, why Europa?
If you stood on Europa's surface, you'd be hit with 5,400 millisieverts of radiation in a single day. That's 1,800 times more than the annual dose here on Earth. If you stay here for a couple hours, you would eventually die from radiation sickness. But Europa contains a secret. When Voyager 1 passed by Jupiter in 1979, it took this photo of Europa. If you compare that to most of the other moons in the solar system, you'll notice something is missing. craters. Every planet and moon has been bombarded by asteroids over billions of years, and most planetary surfaces show it. But not Europa. So why not?
Well, something recent, say over the past 60 million years or so, must have been happening on Europa to erase most of these craters from the surface.
16 years after Voyager, Galileo arrived to Jupiter. It spent 8 years studying both the gas giant and its moons. And Galileo's magnetometer picked up something interesting on Europa. Jupiter's magnetic poles, like Earth's, aren't aligned with its geographic poles. So as the planet rotates every 10 hours, the whole magnetic field wobbles. This changing field from Jupiter induces a magnetic field on Europa, and a relatively strong one at that. That means there must be an electrically conductive layer within Europa that reacts to Jupiter's field. And readings from Galileo indicate that it must be somewhere close to the surface, only tens of kilometers deep.
So what kind of conductive layer?
Well, Europa's white surface is almost entirely covered in a thick crust of water ice. These reddish-brown regions, when observed through a spectrometer, fit the description of a lot of things, like hydrated salts, sulfuric acid, or even bacteria. We need more data to be sure, but recent experiments at JPL found that sea salt, when bombarded with intense radiation, turns from white to this same brownish color found on Europa. So scientists suspect that there's a whole saltwater ocean inside Europa. It could be 100 kilometers deep, meaning Europa would contain twice as much water as the whole of the Earth.
And it must be driving geological activity that constantly smooths out and renews the surface of the moon.
But the Jupiter system only gets about 4% of the sunlight we get here on Earth. So Europa's surface is constantly below negative 160 degrees Celsius. So you'd expect the whole ocean to be frozen solid. But there's a way to generate heat that doesn't rely on the sun. And I've got a little demo here to prove it.
Europa's orbit around Jupiter isn't a perfect circle. This is because Io, Europa, and Ganymede are all in orbital resonance. Each time Ganymede completes one orbit, Europa completes 2, and Io 4. And because of that, Io tugs Europa inward on one side of the orbit, while Ganymede pulls it out on the other, making its orbit more eccentric. Now, Jupiter's pull is stronger on the closer side of the orbit than on the farther side. So Europa is constantly being stretched and squeezed, stretched and squeezed.
And you can see how this rubber ball gets warmer as I squeeze it. Scientists believe that the friction caused by the tidal flexing of the entire moon can generate enough heat to keep the ocean liquid. This effect gets stronger the closer you get to Jupiter, which is why Io is so volcanically active. So you can see this ball is significantly hotter now. I held onto this ball at the same time to make sure it wasn't just the heat coming into my hand.
What sort of temperature of the ocean are we thinking?
So it depends on how salty it is. So melting temperature of ice, or maybe depressed by 10 degrees Celsius below that if it's a very salty ocean. Similar to cold oceans on Earth.
And how would the flexing differ if there's this big liquid ocean versus if there's no ocean?
If there's no ocean, Europa should flex by only about 1 meter in amplitude. But if there's an ocean in there, then it flexes with an amplitude of 30 meters. So that's an enormous deflection, and that will come out pretty clearly in the gravity data. Another argument for how thick the ice shell is, we see these very strange features on the surface that are arcuate in shape, like multiple arcs put together. We call them cycloids, and not something you'd expect to see on an icy moon. And we think they form if a crack propagates at just the right speed, about the speed someone would walk, and is following the changing stress field of Europa being squeezed as it orbits around Jupiter. And if there were no ocean down there, there wouldn't be enough of an amplitude of that motion to explain the cracking. But if there is an ocean, then it could explain the cracking.
All that tidal flexing pushes magma in the outer core up, closer to the seafloor. Water flowing through the crust above it is heated and it picks up minerals from the ground, ejecting them into the ocean. This creates hydrothermal vents. And where we find these on Earth, we also find life. Thousands of meters below the surface with no sunlight, these vents are oases for ocean life. The life forms down here rely on unique bacteria that feed on the minerals from the vents rather than from the energy provided by the sun.
How long are we thinking that Europa has had an ocean?
It could be 4 billion years. We don't know for sure.
That amount of time could give life the opportunity to evolve in those oceans.
Right, exactly right. Organisms can use methane, carbon dioxide, sulfur reactions. Any chemical reaction you can think of that might happen in the ocean can potentially be used as a fuel for that organism's metabolism. So we're not talking about searching for fishes or whales or squids or something down there, but looking for single-celled organisms.
We were so concerned there might be life on Europa that when the Galileo mission was ending in 2003, it was deliberately crashed into Jupiter to avoid the risk of contaminating Europa. But Clipper will not be able to drill through the kilometers-thick ice crust. So how are we going to find evidence for life beneath that thick surface?
This is the Snotbot. It's a drone with petri dishes glued to the top, and it flies right through whale blows to collect whale snot right here on Earth. And zoologists can use the Snotbot to retrieve all sorts of info on a whale's biology. And it turns out we can do something very similar for celestial bodies too. We've actually captured images of water geysers shooting out of Enceladus, a moon of Saturn, housing a subsurface ocean. And the Hubble Space Telescope has picked up some evidence of what could be similar geyser eruptions on Europa. The hope is that Clipper could fly through one of these plumes like the Snotbot and reveal their chemical composition using a mass spectrometer.
But evidence for an ocean on Europa isn't conclusive. Enceladus seems like a stronger candidate. We have actual images of its plumes, and we've even flown through them. We are almost 100% certain there's a subsurface ocean there.
If we have these plumes on Enceladus and there's clearly maybe a liquid ocean there, why does Europa have your attention more than Enceladus? Is there something that draws you?
We don't know how long it takes life to get going, but it's possible that Enceladus may have just kind of started up its engines, whereas Europa has more likely been well evolved over a long time.
Surprisingly, being bombarded by Jupiter's radiation actually makes Europa a better candidate. See, those high-speed particles hitting Europa's surface give water and carbon dioxide molecules enough energy to form new compounds, like formaldehyde or hydrogen peroxide. And these can serve as food for life beneath the surface, if they can get down that far.
And we have evidence of overturn of the icy shell at chaos zones where the icy crust seems to have collided and material has been shoved into the icy shell. So there may be ways for this fuel for life to get down into the icy shell and potentially to the ocean.
And Clipper doesn't have to touch down on the surface to confirm this.
There's an infrared spectrometer to look at the chemical fingerprints of light bounced off the surface to help identify and map out where the salts are, find if there are organics there. There's an ultraviolet spectrograph that's aboard the spacecraft to look for plumes. Are they there? And of course, then can we fly through them? And then there'll be imaging of essentially the whole globe at better than 100 meters per pixel resolution. So one camera will take swaths of images as we fly over the surface, and that's called a wide-angle camera. And then the other camera is the narrow-angle camera. From 50 kilometers altitude, it will get half meter per pixel images, right? So it'll be able to resolve my desk here if it were on Europa. And then it would be a future mission, like a lander, that would go and actually search for signs of life at Europa.
Do you think a lander would have a chance of survival?
There have been studies that say we can get a lander living on the surface for a month if we think that's sufficient to go in there, scoop some stuff up from below the depth of radiation processing, and put it into a mass spectrometer and see what we see.
But the Europa Clipper won't be studying Jupiter's moons alone. The European Space Agency's JUICE mission, or the Jupiter Icy Moons Explorer, is already on its way to Jupiter. It will come to the system just 15 months after Clipper, and it'll even be doing a few flybys of Europa before settling into a tight orbit around Ganymede.
So the European Space Agency will also have a mission there at the same time?
Yes, we're having informal conversations with members of the JUICE science team. What would it mean to have two spacecraft there at the same time? The JUICE mission will end up in orbit around Ganymede, and Ganymede has its own magnetosphere. Well, we'll be outside Ganymede's magnetosphere, so we might say, oh, look, there's this big burst coming from Jupiter, and then JUICE might say, oh, we felt that over here in our magnetic signals. So we wouldn't have to really do anything different except talk to each other and make sure that the sum of the whole is even bigger.
Europa Clipper was scheduled to launch on October 10th, 2024, but NASA is waiting for Hurricane Milton to clear Florida before the spacecraft can take off safely.
When will we get the first results?
We'll start seeing distant observations coming in 2030 as we look at Europa from afar and search for plumes, and then you'll see the first really high-resolution data in 2031.
So after, say, 26 years of thinking about a mission to Europa, how does it feel to be so close to launch?
It's a little surreal, I must say. This has been such a long time coming. It's occasionally hitting me that our spacecraft is going to be up there in the heavens, right, on its way.
It turns out that during a Europa Ocean conference in the late 90s, NASA actually video called Arthur C. Clarke, and after showing him plans for a future mission to explore the faraway ocean world, Clarke finally gave NASA permission to land on Europa.
Europa Clipper is a perfect example of the amazing things we can do when we set ourselves ambitious goals and then work together with others to achieve them. But I think we often get wrapped up in our everyday lives and forget just how much of an impact we can make on the world. That's true on a society-wide level like these big international space missions, but I also think it's true at an individual level. You yourself can probably accomplish much more than you think when it comes to making the world a better place. And today's sponsor, 80,000 Hours, wants to help you do just that. They are not selling anything. 80,000 Hours is a non-profit that can help you work out a plan for achieving a big positive impact on the world and then executing on it. Career advice typically aims to help you find a job that suits your preferences. But what if you really care about helping the world? Well, sure, they can tell you to be a doctor or a teacher, but these aren't your only options, which is why 80,000 Hours have done over 10 years of research into how to find a career that does a lot of good and also feels satisfying. They have everything from an in-depth career guide to a podcast on the world's most pressing problems and how we can solve them. They even have a curated job board with hundreds of high-impact career opportunities. And everything they provide is free forever. So if you want to make a difference with the 80,000 hours you have to shape your career, then sign up now at 80,000hours.org/Verit.
Nothing gets in. No one gets out.
In carnage, I bloom like a flower in the dawn.
Vladislav Sirik in the flesh.
What?
You can never see anything enter a black hole. Imagine you trap your nemesis in a rocket ship and blast him off towards a black hole. He looks back at you, shaking his fist at a constant rate. As he zooms in, gravity gets stronger, so you'd expect him to speed up. But that is not what you see. Instead, the rocket ship appears to be slowing down. Not only that, he also appears to be shaking his fist slower and slower. That's because, from your perspective, his time is slowing down. At the very instant when he should cross the event horizon, the point beyond which not even light can escape, he and his rocket ship do not disappear. Instead, they seem to stop, frozen in time. The light from the spaceship gets dimmer and redder until it completely fades from view. This is how any object would look crossing the event horizon. Light is still coming from the point where he crossed, it's just too redshifted to see. But if you could see that light, then in theory you would see everything that has ever fallen into the black hole frozen on its horizon, including the star that formed it. But in practice, photons are emitted at discrete intervals, so there will be a last photon emitted outside the horizon, and therefore these images will fade after some time.
This is just one of the strange results that comes out of the general theory of relativity, our current best theory of gravity. The first solution of Einstein's equations predicted not only black holes, but also their opposite, white holes. It also implied the existence of parallel universes and even possibly a way to travel between them. This is a video about the real science of black holes, white holes, and wormholes.
The general theory of relativity arose at least in part due to a fundamental flaw in Newtonian gravity. In the 1600s, Isaac Newton contemplated how an apple falls to the ground, how the moon orbits the Earth and Earth orbits the sun, and he concluded that every object with mass must attract every other. But Newton was troubled by his own theory. How could masses separated by such vast distances apply a force on each other? He wrote that one body may act upon another at a distance through a vacuum without the mediation of anything else is to me so great an absurdity that I believe no man who has a competent faculty of thinking could ever fall into it. One man who definitely had a competent faculty of thinking was Albert Einstein, and over 200 years later, he figured out how gravity is mediated. Bodies do not exert forces on each other directly. Instead, a mass like the sun curves the space-time in its immediate vicinity. This then curves the space-time around it, and so on all the way to the Earth. So the Earth orbits the sun because the space-time Earth is passing through is curved.
Masses are affected by the local curvature of space-time, so no action at a distance is required. Mathematically, this is described by Einstein's field equations.
Can you write down the Einstein field equation?
This was the result of Einstein's decade of hard work after special relativity. And essentially what we've got in the field equations, on one side it says, tell me about the distribution of matter and energy. The other side tells you what the resulting curvature of space-time is from that distribution of matter and energy. And it's a single line. It looks like, oh, this is a simple equation, right? But it's not really one equation. It's a family of equations. And to make life more difficult, they are coupled equations, so they depend upon each other, and they are differential equations, so it means that there are integrals that have to be done, So there's a whole bunch of steps that you need to do to solve the field equation.
To see what a solution to these equations would look like, we need a tool to understand space-time.
So imagine you're floating around in empty space. A flash of light goes off above your head and spreads out in all directions. Now, your entire future, anything that can and will ever happen to you, will occur within this bubble, because the only way to get out of it would be to travel faster than light. In 2 dimensions, this bubble is just a growing circle. If we allow time to run up the screen and take snapshots at regular intervals, then this light bubble traces out a cone, your future light cone. By convention, the axes are scaled so that light rays always travel at 45 degrees.
This cone reveals the only region of spacetime that you can ever hope to explore and influence. Now imagine that instead of a flash of light above your head, those photons were actually traveling in from all corners of the universe, and they met at that instant and then continued traveling on in their separate directions. Well, in that case, then into the past, these photons also reveal a light cone, your past light cone. Only events that happened inside this cone could have affected you up to the present moment. We can simplify this diagram even further by plotting just one spatial and one time dimension. This is the space-time diagram of empty space. If you want to measure how far apart two events are in space-time, you use something called the space-time interval. The interval squared is equal to minus dt squared plus dx squared. Since space-time is flat, the geometry is the same everywhere, and so this formula holds throughout the entire diagram, which makes it really easy to measure the separation between any two events. But around a mass, space-time is curved, and therefore you need to modify the equation to take into account the geometry.
This is what solutions to Einstein's equations are like. They tell you how space-time curves and how to measure the separation between two events in that curved geometry.
Einstein published his equations in 1915 during the First World War, but he couldn't find an exact solution. Luckily, a copy of his paper made its way to the Eastern Front, where Germany was fighting Russia. Stationed there was one of the best astrophysicists of the time, Karl Schwarzschild. Despite being 41 years old, he had volunteered to calculate artillery trajectories for the German army.
At least until a greater challenge caught his attention: how to solve Einstein's field equations.
Schwarzschild did the standard physicist thing and imagined the simplest possible scenario, an eternal static universe with nothing in it except a single spherically symmetric point mass. This mass was electrically neutral and not rotating. Since this was the only feature of his universe, he measured everything using spherical coordinates relative to the center of this mass. So r is the radius, and theta and phi give the angles. For his time coordinate, he chose time as being measured by someone far away from the mass, where spacetime is essentially flat. Using this approach, Schwarzschild found the first non-trivial solution to Einstein's equations, which nowadays we write like this. This Schwarzschild metric describes how spacetime curves outside of the mass. It's pretty simple and makes intuitive sense. Far away from the mass, spacetime is nearly flat, but as you get closer and closer to it, spacetime becomes more and more curved, it attracts objects in, and time runs slower. Schwarzschild sent his solution to Einstein, concluding with, "The war treated me kindly enough, in spite of the heavy gunfire, to allow me to get away from it all and take this walk in the land of your ideas." Einstein replied, "I have read your paper with the utmost interest. I had not expected that one could formulate the exact solution to the problem in such a simple way." But what seemed at first quite simple soon became more complicated. Shortly after Schwarzschild's solution was published, people noticed two problem spots. At the center of the mass, at r equals 0, this term is divided by 0, so it blows up to infinity, and therefore this equation breaks down and it can no longer describe what's physically happening. This is what's called a singularity. Maybe that point could be excused because it's in the middle of the mass, but there's another problem spot outside of it. At a special distance from the center, known as the Schwarzschild radius, this term blows up. So there is a second singularity. What is going on here? Well, at the Schwarzschild radius, the spacetime curvature becomes so steep that the escape velocity, the speed that anything would need to leave there, is the speed of light. And that would mean that inside the Schwarzschild radius, nothing, not even light, would be able to escape. So you'd have this dark object that swallows up matter and light, a black hole, if you will.
But most scientists doubted that such an object could exist because it would require a lot of mass to collapse down into a tiny space.
How could that possibly ever happen? Astronomers at the time were studying what happens at the end of a star's life. During its lifetime, the inward force of gravity is balanced by the outward radiation pressure created by the energy released through nuclear fusion. But when the fuel runs out, the radiation pressure drops, so gravity pulls all the star material inwards. But how far? Most astronomers believed some physical process would hold it up. And in 1926, Ralph Fowler came up with a possible mechanism. Pauli's exclusion principle states that fermions, like electrons, cannot occupy the same state. So as matter gets pushed closer and closer together, the electrons each occupy their own tiny volumes. But Heisenberg's uncertainty principle says that you can't know the position and momentum of a particle with absolute certainty. So as the particles become more and more constrained in space, the uncertainty in their momentum, and hence their velocity, must go up. So the more a star is compressed, the faster electrons will wiggle around, and that creates an outward pressure. This electron degeneracy pressure would prevent the star from collapsing completely. Instead, it would form a white dwarf with a density much higher than a normal star. And remarkably enough, astronomers had observed stars that fit this description. One of them was Sirius B. But the relief from this discovery was short-lived. 4 years later, 19-year-old Subrahmanyan Chandrasekhar traveled by boat to England to study with Fowler and Arthur Eddington, one of the most revered scientists of the time. During his voyage, Chandrasekhar realized that electron degeneracy pressure has its limits. Electrons can wiggle faster and faster, but only up to the speed of light. That means this effect can only support stars up to a certain mass, the Chandrasekhar limit. Beyond this, Chandrasekhar believed not even electron degeneracy pressure could prevent the star from collapsing. But Eddington was not impressed. He publicly blasted Chandrasekhar, saying, "There should be a law of nature to prevent a star from behaving in this absurd way."
And indeed, scientists did discover a way that stars heavier than the Chandrasekhar limit could support themselves.
When a star collapses beyond a white dwarf, electrons and protons fuse together to form neutrinos and neutrons. These neutrons are also fermions, but with nearly 2,000 times the mass of an electron, their degeneracy pressure is even stronger. So this is what holds up neutron stars.
There was this conviction among scientists that even if we didn't know the mechanism, something would prevent a star from collapsing into a single point and forming a black hole. Because black holes were just too preposterous to be real.
The big blow to this belief came in the late 1930s, when J. Robert Oppenheimer and George Volkoff found that neutron stars also have a maximum mass. Shortly after, Oppenheimer and Hartland Snyder showed that for the heaviest stars, there is nothing left to save them when their fuel runs out. They wrote, "This contraction will continue indefinitely." But Einstein still couldn't believe it. Oppenheimer was saying that stars can collapse indefinitely, but when Einstein looked at the math, he found that time freezes on the horizon, so it seemed like nothing could ever enter, which suggested that either there's something we don't understand, or that black holes can't exist.
Oppenheimer offered a solution to the problem. He said, to an outside observer, you could never see anything go in, but if you were traveling across the event horizon, you wouldn't notice anything unusual, and you'd go right past it without even knowing it. So how is this possible?
We need a space-time diagram of a black hole. On the left is the singularity at r equals 0. The dotted line at r equals 2m is the event horizon. Since the black hole doesn't move, these lines go straight up in time. Now let's see how ingoing and outgoing light rays travel in this curved geometry. When you're really far away, the future light cones are at the usual 45 degrees. But as you get closer to the horizon, the light cones get narrower and narrower, until right at the event horizon, they're so narrow that they point straight up. And inside the horizon, the light cones tip to the left. But something strange happens with ingoing light rays.
They fall in, but they don't get to r equals 2m. They actually asymptote to that value as time goes to infinity. But they don't end at infinity, right? Mathematically, they are connected and come back in, and they're traveling in this direction. And this bothered a lot of people. This bothered people like Einstein because he looked at these equations and went, well, if nothing can cross this sort of boundary, then how could there be black holes? How could black holes even form?
So what is going on here? Well, what's important to recognize is that this diagram is a projection. It's basically a 2D map of four-dimensional curved space-time.
It's just like projecting the 3D Earth onto a 2D map. When you do that, you always get distortions. There is no perfectly accurate way to map the Earth onto a 2D surface. But different maps can be useful for different purposes. For example, if you want to keep angles and shapes the same, like if you're sailing across the ocean and you need to find your bearings, you can use the Mercator projection. That's the one Google Maps uses. A downside is that it misrepresents sizes. Africa and Greenland look about the same size, but Africa is actually around 14 times larger. The Gall-Peters projection keeps relative sizes accurate, but as a result, angles and shapes are distorted.
In a similar way, we can make different projections of 4D spacetime to study different properties of it. Physical reality doesn't change, but the way the map describes it does.
He had chosen to put a particular coordinate system over space and have a time coordinate. And off you go. It was the most sensible thing to do, right?
People realize that if you choose a different coordinate system by doing a coordinate substitution, then the singularity at the event horizon disappears.
It goes away. That problem goes away. And things can actually cross into the black hole.
What this tells us is that there is no real physical singularity at the event horizon. It just resulted from a poor choice of coordinate system. Another way to visualize what's going on is by describing space as flowing in towards the black hole, like a waterfall. As you get closer, space starts flowing in faster and faster. Photons emitted by the spaceship have to swim against this flow, and this becomes harder and harder the closer you get. Photons emitted just outside the horizon can barely make it out, but it takes longer and longer. At the horizon, space falls in as fast as the photons are swimming. So, if the horizon had a finite width, then photons would get stuck here. Photons
Hola, Kakarot. Soy Vegeta, el príncipe de todos los Saiyans. Vegeta, you do not speak Spanish. What are you doing? Estoy celebrando la batalla de Puebla del 5 de mayo. I could have guessed that.
down. Enemy double kill.
The clock.
An enemy has been slain.
Steady. I never miss.
An ally has been slain. An enemy has been slain. Double kill.
Headshot.
has been slain. Rampage. An ally has been slain.
You should have considered your actions.
Double kill. has been slain. An enemy has been slain.
I've got you under my skin.
Your team has destroyed a turret. Enemy pentakill. Shut down. Ace. Your turret has been destroyed. Aced. The enemy's inhibitor has respawned. Your team has destroyed an inhibitor.
Mind the trap.
Has been slain.
A harvest moon, so aptly.
Double kill.
I'm not big on sermons. Broken bones teach better lessons.
Right here. Wait.
I like
Losing
this.
someone is
I should buy everyone.
honoring their memory.
Minions have spawned.
No love. My God, demand.
An enemy has been slain.
Bearded lady, Nagake Boros, names
Hope to
don't
see you
matter.
again soon.
Double kill.
Divide and conquer.
Triple kill. Shut down.
Baby, are
Been slain.
Minigun. Evil? Why should it ever
An enemy has been slain. enemy double kill. An ally has been slain.
Notice
It is not what we have.
new spirit
It is what we
blossoms?
can throw away.
I smell a
An enemy has been slain. Killing spree. An ally has been slain. Shut down.
one round to another.
Enemy has been slain. Double kill. An enemy has been slain.
When I am done with this, it will make a fine offer.
The other merchants will be so
Your team has
jealous.
destroyed a turret.
Enjoy the festivities.
An ally has been slain. An enemy has been slain. Unlocked.
It is our desire.
An enemy has been slain.
Hello, dears. What would you like?
Here we are. An enemy has been slain.
Wisdom is frequently a kick in the head.
Come back if you need more.
Nagasho.
Shut down. Enemy has been slain.
Everyone has a plan until they get
Love me
punched in
as
the face.
Has been slain.
Life is too short.
Enemy killing spree. Shut down.
They must be twisted to grow. Look at them. Without change, something kills in
Keep an eye out for any mysteries.
Ace.
How did I love only
Welcome
one
back,
man?
fellow travelers.
An enemy has been slain. Your team has destroyed a turret. Your team has destroyed an inhibitor. An ally has been slain.
They run, or I bleed them.
An ally has been slain. Double kill.
What the festival remains
Ace.
strange energy in the air.
你抱我吻上我嘴巴，似你吻向他。
Your team has destroyed a turret.
I am a teacher. Build what we learn.
Has destroyed a turret. An enemy has been slain. An ally has been slain. Rampage. Double kill. Haste. An enemy has been slain. Haste.
It is the storm.
It is
that
a
is
joy
life.
to see you again.
Only what moves.
That's a
Only
favorite
what moves.
Well,
Victory!
你抱我吻上我嘴巴，獨自你吻向我，我暗中想總有一點愛吧，可以交給我吧，總算得戀愛。是怕有念一個人太深刻，愛就愛了，不怕沒來過。
How about a magic trick? Oblivion awaits. Without question.
Minions have spawned. Enemy double kill. Triple kill.
has been slain. Enemy killing spree. In due course. Killing spree.
Never fall.
Ace. Shut down.
Their destruction.
Enemy rampage.
Not even
An enemy has been slain. Double kill. Never fall. An ally has been slain. Your turret has been destroyed. An ally has been
Never
Your turret has been destroyed. Your turret has been destroyed. An enemy has been slain.
How about a drink?
Minions have spawned.
To shake or not to shake.
Never fall. Sa ela sa. Never falter.
It's nearly time.
Shut down.
Never falter. Never falter. An enemy has been slain.
On my way.
Never falter.
Enemy double kill. Enemy has been slain. An ally has been slain. Enemy has been slain. Enemy killing spree.
On my way.
Headshot.
Enemy double kill. Enemy triple kill.
It's nearly time.
Slain enemy. Killing spree. Shut down. Ace. Double kill. An ally has been slain. An enemy has been slain. Double kill. been slain.
It's nearly time.
Slain an enemy. Ace. Enemy double kill. I hear you. Aced. An enemy has been slain. Never fall.
like it, go pick up a two. Freestyle to go done with the dude. Fresh you got beat, like it for food. Bitch, get up and give me some head.
time has come to prune the tree.
The balance of power must be preserved.
Cô dâu của nô
From the fall.
Killing spree. Your turret has been destroyed. An enemy has been slain. Shut down. An ally has been slain. An ally has been slain. An ally has been slain.
Give up trying to stop. I can understand their position.
Justice will be served.
Enemy killing spree. An enemy has been slain. Your team has destroyed a turret. An enemy has been slain.
Just for you. Light on my path. Here I come.
An enemy has been slain. An enemy has been slain. Has been slain.
Bring us.
Has been slain. Your team has destroyed a turret. You have slain an enemy. Enemy double kill. turret has been destroyed. Has been slain.
Porque en verdad rompieron.
Trong bóng đêm anh chỉ còn thấy bóng đêm. Nhìn vào mắt em anh thấy hai cái chòm đen.
Don't stop, say the N-word, don't
Epstein, fuck niggers! Choose.